Okay. So we have seen the Black-Scholes formula, but the second part of the tutorial will be on the pricing of an American put option. As we have learned, American call option is the same as American put. So in order also to show you how powerful the binomial or binomial tree is. So we have figured out how do we get the price. Theoretically, it's the execution time is the time when the Snell envelope hits first time the payout function. And the Snell envelope we have calculated at the maximum of the payout and the future expectation of the Snell envelope next time by starting at time capital N. This we will now do on the CIR model. So that's an implementation of the Snell envelope I showed you before. So before we can also, of course, prove that's the optimal strategy, but I try to convince you that that's good to do it like this, calculate this one. Okay, in order to pricing on a tree, what you first do, you just generate the tree. This means it's a forward step. You generate going up and down the values. And then you, what you do first, I think the picture should be also still here. So this, it's 3 steps. You start with 100, you go up, 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 down, 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 down. This is now n steps, of course, n equals 3. It's a joke. You have to do more in real life. But so this is one possible path of your asset value. You go up from 100 to 112, and then you go up 100, but you might go down in the last step to 112. So you have 4 potentials. That's a binomial distribution coming from a binomial. You have 4 steps. So that's a forward step. Forward steps means you go this up, 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 up. It's one case. You go up, down, then up. So you calculate these boxes first. Price of asset. And our specification here. Best thing you learn, you write down these parameters and then do it yourself. Or tell the computer to do it. I don't know whether you can learn from coding, but whatever. Up is sigma is 20%, and that's a reasonable assumption on the yearly volatility is actually 20%. So let's say that's 3 years. That's okay. That's a 3-year option. Volatility is, and then you e to the power minus is this one. You calculate e minus sigma plus sigma 1 plus e plus sigma and 1 plus e minus sigma. Okay, so that's our CRR tree with the parameter sigma, interest rate 6%, and that, okay, 1/3, so that the volatility is a little high. So no, we have 3 trading days. Nevertheless, it's our tree. It's going up and down. So these values you should recalculate. That's the first step you do. Can somebody verify the numbers? Okay. Okay, what we do next, because we go backward, yeah. So again, our set n, yeah, this is what we have done. Calculate the share price each node. Determine the P of at the maturity n. We're going backward. We start with the final time. And so we calculate the value at time n. This we have done. Because it's higher than 100, what is our strike? It's my strike. If no strike is mentioned, usually the strike is current value, so it's 100. Let's check it whether it's 100. Yeah. No? So it's falling in two scenarios. The put is in the money at the end. So this is 100 minus 89. You understand? That's the first step. It's in any option pricing, you do it like this. In any tree-based option pricing. Okay, if you are, you bought a put because you believe, very pessimistic, everything is going down. I want to make money from equities going down. And you make money. In these two scenarios, you make money. You put 10.9 in this scenario. There you have just 2 downs and 1 up. Down, up, down. Okay. So, and if it's even worse, you have 2 times down, or 1, 2, 3 times down. Your put is very valuable. It will pay you 29.28. But only if you didn't execute before. Because in American option, you could have executed before. Okay. Now, so at the end, you didn't execute, that would be your payout.
Sir, this
Then you go
can also be
backwards.
applied to American option.
This is an American option. We are pricing an American option.
Okay, sir.
Yeah.
Okay, sir.
Yeah. If you didn't price it here, so that's your set n. Yeah.
Yes, sir.
So your set n was defined at the maximum of your P out and your expectation of Zn plus 1 given Fn. And Zn equals Xn. So this means if you execute our Xn, in our case is always the maximum of K minus Sn, the asset and 0. If you say at time n, I want to execute my option, you get this amount of money. This means Zn equals Xn equals, here you have capital N. Now you got Zn equals max K minus Sn, 0. That's the definition of the snare. Okay, now you go backward. So this means you go to one of the nodes. And then what you do, then you have this non-execution. If you didn't execute, and then your Now, as we take the two neighboring, at time, you are now at two upward, you have two upward moves. You now move backward. That's why I don't like online teaching, because all screens are too small. You are now here. So the value, you have to calculate the expectation of Zn plus 1 Fn, and the case, this is called non-execution. If you don't execute here, the value is a discounted cash flow from the cash flows after this one. So you take the risk neutral probability here. Go backward. If you don't execute, this is, then you only have get the value one time later. In the case, if it's F index n minus 1, 2 points up, you are exactly here. Sorry. Now you have to calculate two values here. The value, now, of course, the non-execution value is 0 here because you just have 0, but also the execution value is 0. So it's clear here everything remains 0 in this case. Because asset value is 125.98. I want now to execute my option. Bank is happy, tells, okay, please execute. Delete your contract, but I don't pay you nothing. And in addition, you also know if you wait, you also don't get nothing. So the value is 0 of your put option. Okay, here it's different. Here you pay out. If you say now, yes, I want to execute, it's again 0. But if you calculate the average price of this with P star times this one plus 1 minus P star this one, you get 4.76. That's the value of the put option here. And of course here, what's the value of the put option? Here the execution, if you execute, you get 11. You get 26.2 probably. That's some rounding error here. So you should execute here, because the average of these two is smaller. This 4.26, you see it's calculated. Let me see whether you can see it. After 2 steps, how do you come here? Up. 2 time 2 is actually time 3. 1, 2, you went 1 up and down. Now you have this one. You calculate the put value is 0, because 100 is a strike, and the non-execution value is, you take the put here and you multiply it 1 minus P star, you discounted it. And that's 4.76. At 0, you see the non-execution at this point here, we are calculating this one. So the Snell envelope will have the value, non-execution, the discounted expectation of the future states. There are only two. It's 29, 20 times 28. If it's going down and it's going up, it's P star times this one. And of course, the discounting is like this. Then you get 18.71. So this means here to wait and not to execute gives you less money than to immediately execute. Okay, now then we go down further, and so the final option price is 6.18, and you see you should execute your execution time. You can also calculate from this one. So you have now to calculate, you have to average over all this to get the one where you have the your Snell envelope meet the underlying asset. Yeah, and you execute first time. Yeah, this means you have to calculate all these values. You have in each node you have to calculate. You have to calculate these values. If the execution is executed, your yes value is this one, and you execute as soon. If you are now at a point I and state J. This you can calculate. This you have done. Now you can calculate if non-execution is worse than execution. And then you execute. This means on this tree, in order to know when you execute, you have to report, which is your homework, to calculate not only P, but to calculate the two ingredients of P. And at each point in time and space where you are, you know whether you execute or not. Like, do you want to execute at the beginning? Your execution gives you 0. Your prolongation, in this it's trivial, gives you 6.81. Here you don't execute. Don't execute immediately because execution gives you nothing, but your option value is positive. I mean, that's always the case. If you write the option, don't execute. Yet this time you have to know how you got the 2.08 and how you get the 11.59. Here, of course, you know execution gives you, I mean, it's not recorded here, but here, what you know. Here, if you execute, you get nothing, you stay. If it's going up, you stay, you don't execute. It's clear because you bet it on going down. But what are you doing here? Here you know, okay, your non-execution, your execution will give you 11.59. And this calculation showed you that's more. No, this is only 10. So here you still have to go because the value is 11.59 of the option, but the execution only gives you 10.9. Here you go on. So in order to know whether you execute, you have to know these two values, non-execution value and execution value. Yeah. Yeah, and if you do the same now with no execution, you can only execute at the end. You do the calculation, so you get the European option price. And you see that the European option price is for 5.82. That's what so in this case, the American feature is valuable for you because you execute early. Okay. And also this simple example shows you how to do this if you have 1,000 steps or whatever. This you should be able to program. I'm not able to program this, but you should be able to program this. Okay. I think we are now coming. Okay, the Greeks, what's called the delta, but we come to this if we go in the black school setting. Yeah, okay. Now, okay, we can do some examples of options you have in real life. Yeah. I mean, we come later to the sensitivities if we have done continuous time, continuous time mathematical continuous markets. Yeah? So there are many other traded options. Yeah, one is the payoff. It's called down and out calls. This means you only execute your call option if the price always stayed above a level H. Why do you want to do it? Basically, that's cheaper for you than without this restriction, because the bank just don't pay if in between the asset value has fallen. You have this level H, that's now time here. You have the level H, your asset price, and if it's falling down here, option pays you nothing. Only all paths which are above, this is a good path here, always stays above, then you finally get a payout depending on which level you are. Let's say you are here, and it's a maturity, you get this as a payout. Payoff. In this case, when it's going down, so there are less scenarios where you get money. So if the bank is fair, bank doesn't account for these events where they don't have to pay, so it's cheaper for you. And you're anyway optimistic. You don't think, because you bought a call, which makes money if asset goes up. You're just thinking, okay, that's fine. I pay less money for an event where I don't believe in this, what's called option strategy, if you like, the volatility strategies. Yeah, I make money anyway because I'm convinced it's going up and the price is less. If I have in my contract, I have also written, okay, if it's below H, you don't have to pay me nothing. Option expires. No, but you can also say, okay, I only want to get the money if at some point in time before it falls below H. Or you can say, okay, that's another option strategy. Or you just want to get your payout age only if it's below. Huh? Huh? Yeah, you are very optimistic. Yeah, you say, okay, anyway, yeah, I just put it like here. I start here in my age here, yeah, and I only want to have a payout if it's going above. If it's going above some point in time, it's going above age. Yeah? This means you are very optimistic. Yeah? Let's say that's also age is also an option call payout. Yeah? You have different ways to formulate your opinion on the market by investing in options like this. And you can say, okay, for some scenarios, like in this case, I don't believe it's going down. I don't want to pay for this anyway. Okay, these are kind of simple. And you see, what you see here actually, that's all path dependent. The exit, and that's quite common that you have path dependency. That you have in your option contract, you have additional features which are path dependent. Then we have digital options here because there was a market of digital options. Now, for example, your age is constant C, you mean, okay, if the, let's say the BioNTech equity share stays below 500 until the year, until end of 2026, I want to have 10 euros. You can, it's a digital, yeah. It's an event where you get just, you are just betting that BioNTech share will stay below a certain level. They have all different names, up and out call. And then you can have, you want to buy the option at the minimal price. This means that's kind of not adapted, but that's not necessary. You can wait until T and then say, okay, I buy it at this price. Or I sell it. Or it might depend your payout. Like that's quite often in mortgages, where you can make a contract that you get the lowest interest rate over the next period of time. And look back call, that's similar. You just say, okay, that's also just, you see that's all functions which depends on the entire evolution of the equity price. And you can buy this from a bank if you like. Or Asian options, you compare the final value from the average of the price during time, or you have a strike. These are exotic path-dependent options. So in the case of it's always this tree method, it's very robust. You can easily calculate with the same procedure as we have seen in the put. Execution. You don't have to do this non-execution because it's in this sense a European option, but that's your cash flow you get anytime you get, so you can recalculate the price. I mean, I didn't present it for the call option, but the call option is the same as in the put, only that you cannot execute. You start final price and then you take expectation stepwise going down to the final expectation. That's you apply, you work more or less on the martingale property that at the end, after going backwards, you get the actual price. Yeah, so backward induction is more or less always, yeah? Backward induction means mathematically you see, okay, your hedge portfolio is a martingale. This means you take successive expectation. That's a martingale property. That's a discounted martingale property. Then you go backward, so you get your price, and then you go back, takes in the expectation of this one, given ft minus 2, you get v tilde t minus 2 going down to v 0. That's a backward induction on the binomial tree, which was hidden in this one theory. Numerically, it's like going through the tree, but of course that's only in the simple model, but you can take the simple model as an approximation of a more complex model. And then you know your VT, and the VT is always a fair price. You don't have, so that's the martingale property is more or less a recursion, how to get from the final P out the current price. And this is, for this you need martingales. Okay. The Black-Scholes model. This tutorial was actually on Black-Scholes model already, so we now are a little bit behind. So Black-Scholes model is based on Brownian motion. Again, who have heard about Brownian motion?
Yes, sir. I have heard.
Yes, sir.
Yeah. Okay, Brownian motion is, so Brownian motion, it's a continuous time stochastic process denoted as B here. And it has a property, what we assume is that it has continuous path. And it has a property that the increments are independent. And for all increments, the distribution is normal distributed. This means 0 and variance t minus s. Okay. Because to some extent we have already seen that zero sets, because we have this equivalent martingale measures. The one technical thing is here that we put all subsets of zero sets into the sigma algebra. This is called augmentation of the natural filtration. That way we don't take the natural filtration adapted to BT, but we put in all zero sets. Okay. And so the financial markets we have, that's ST, which solve this stochastic differential equation, if you like. So that's the simplest, let's say, the simplest positive process is more or less a Brownian motion taking to the exponential. This means the log of this one is normal distributed. This you see because the solution of this equation 4.1 is this one. So our ST is called a geometric Brownian motion. Actually, if it just takes a log of this one, you get a Brownian motion with volatility sigma and drift mu minus s square half times t. It's not driftless. So the log of this is kind of a Brownian motion with a drift. So who knows how to get from 4.1 to 4.2?
Yes, sir, I know.
You know, it's done by who else? No? So that's E2 formula or stochastic calculus is already in here. No? Because let's say we have mu equals 0. What's written here is dst equals sigma st dbt. Yeah? So what you would expect in standard calculus, it is just e to sigma bt. But that's wrong. You see, that's not standard calculus. That's stochastic calculus. It's important to note this because even if mu equals 0, you have this correction term. And that's based on E2's formula. The E2's formula is very important, and I will also give it at some point in time. But let's now see what our ST, it is also continuous path, and for each fixed t, it's a log normal distributed. This means the log of ST is normal distributed. Of course, it's not standard normal, it has some parameters. The parameters, the mean is mu minus sigma squared times t, that's the expectation. And the volatility is, if you take the log, the log of ST as a normal distribution, log of ST. It's a normal distribution.
Sir,
yeah.
Excuse me, sir. Sir, why is geometric Brownian motion needed for asset? Why not only Brownian motion?
Because Brownian motion itself takes negative values. You don't assume that there's also the ST is positive because it's exponential of something. It's positive.
Okay, sir. Another question is that it follows the log normal distribution, but in real scenario, there may be a possibility that it does not follow a normal distribution. There may be some skewness.
Yeah, of course. In reality, you can, if you do it like, you can take Levy processes. You can say it's a log Levy process. Then you have, I mean, depends which type of, whether you want to have that the STs, the returns are independent of F, then you have a stationary process. This means it's a Levy. More general, you can say ST equals E to the power Levy process. It depends. So you can be more exact. You can take any other type of stochastic equation here. This comes from this assumption. You can, of course, see, why do I still have red? You can take your favorite DST. It can even be a function, call it MST TDT. Best is always to have positive, it's proportional. You can make it as you like. But of course, then you don't have closed form solution. We know in stochastic analysis that you always have, there's a diffusion, the general diffusion. So in D equals 1, only one risky asset, you have a full-blown solution theory of this. You can get the law of this one, which you finally need. Still, that's why we did the abstract theory. Still, if you figure out that you have a martingale measure here, then you do the expectation of the P out evaluated, let's say, at S capital T. So you need to do this properly. To analyze this, you need some knowledge about ST. And as I said, in some cases, you can solve it. In some other, I mean, typically, if you have an Ornstein-Uhlenbeck process, it's something like mu theta minus with mean reversion. That's always quite often. You have something like this. And then you might even have sigma, for example, square root of ST dBT. This gives you also a positive process if you like. You can also do statistical analysis. If you do statistical analysis, then usually you assume that your ST equals E to LT, where LT is a Levy process. Then you can have gamma distribution, several kinds of distribution, hyperbolic distribution. ST is hyperbolic. Or log of ST is hyperbolic. But that's an entire slew of distributions which can be somehow realized by stochastic processes. That's the most literature you find on Levy processes. Because in Levy processes, you somehow know the distribution semi-explicitly, or at least you can calculate Laplace transforms and so on. I mean, if, as I said, you want to calculate these expectations. For pricing, you have to calculate the expectations. It's always the same. You always take pricing is always taking expectation of some function. If it's simple, of ST under Risch-Neutral measure, then you need to know the distribution of ST. In many cases, what you get the Laplace transform, and from the Laplace transform, I mean, you have to use all your tools you from probability theory and from theory of stochastic process to get a handover on this. Then you do fast Fourier transform, if you like, numerics, and get the distribution. You get a formula for this one quite often, like a Fourier transform. And there are several ways. But just to start just with statistical analysis of asset returns and don't have a stochastic process is a kind of short reaching, because I mean, you need the dynamics. You need to embed it in a dynamic. Just to have distribution as single point in times, I mean, it's not only uncertain, it's also dynamic. But as I said, you can realize many distributions or many stylized features of distributions. You have, let's say, skewness or whatever, like the normal inverse Gaussian distribution, which is also a Levy distribution. Hyperbolic distribution is a large, I don't know, you have 5 or 6 parameters for this distribution. I mean, you can fit more or less all than one-dimensional distribution you like. As I said, you can take jump diffusion. Base for a jump diffusion. Then you have DST. It's something that drift, which might be state dependent or not. DT, and you have your Brownian motion, stochastic integral with respect to Brownian motion, dW, BT, and you have another one which is, let's say, more complex, but it's actually path space, and you have a Poisson process, and you still have to have a drift of the Poisson process. Now that's the simplest jump. The Poisson process, which again has parameters like waiting time for the next jumps, and then you had usually it's called H, which might also depend on T and ST. You have a stochastic differential equation with a jump part. A jump diffusion. But so that's kind of very big zoo or big toolbox of handles. The main topic of this class is to understand the basic topics, which you will apply in every other. All others is just more probability theory, more statistics. The essential feature is of mathematical finance is to understand this risk-neutral pricing, martingale measures, martingales. That's a very important tool. Okay, but this, as I said, we will do then for our Black-Scholes model and see how the Black-Scholes model also in this setting appears from the basic principle of non-arbitrage pricing, which is also called arbitrage pricing, but basically it's non-arbitrage pricing, and from replication. You have always the same. Also the replication, you have to do stochastic calculus for jump processes, and you have to show that there is a representation theorem also for, or there's a unique martingale measure, whatever bit of the general theory you want to apply. So I guess it's a good point in time to finish this lecture. So we will come together tomorrow.
Yes, sir. Yes, sir. So tomorrow at 11:30 Indian time. So it's 8 a.m. German time. We'll meet again tomorrow. Thank you so much, sir, for this wonderful lecture.